Our last example of a three-dimensional dynamical system is the very beautiful Lorenz model. Now, the Lorenz model was invented as an idealized description of large-scale atmospheric flows. So to give a sense of what we're talking about, let me just draw for you a very simple scenario. It's a nice summer day somewhere in the Great Plains. There's no weather systems coming through. The sun comes up, it's beautifully sunny, there's no wind, there's no clouds in the sky. And by 10 o'clock in the morning, even though there's obviously going to be no rain and no weather systems coming through, one sees rows of fluffy cumulus clouds in the atmosphere. What is causing this? So the sun is up in the sky and it's warming the atmosphere. There is a temperature gradient in which the air near the ground is warmer than the air higher up. So here's the ground. And here are cumulus clouds with roughly flat bottoms and with sort of fluffy tops. And the point is that when there is sufficient temperature gradient, there is large-scale convection instability set up such that air is rising where the clouds are and is actually falling in the region between the clouds. So the convection rolls look something like this schematically. Now, to understand the dynamics of these convection rolls is a state-of-the-art problem in fluid dynamics. One has to understand both the evolution of the velocity field and the temperature field in the system. And the beauty of the Lorenz model is that one extracts from this complicated nonlinear set of coupled differential equations a set of three coupled ordinary differential equations that encapsulate some of the basic phenomena of these large-scale convection rolls. And so that is the basic idea of the Lorenz model. So I'm not going to present any of the analysis. It starts with the basic fluid dynamics and then reduces it to this Lorenz model, but I'll just write down the equations of motion themselves and describe what are the variables and what are the parameters that enter into the Lorenz equations. So the Lorenz equations are a set of three coupled differential equations for three variables x, y, and z. And these equations are x dot is equal to sigma y minus x. Y dot is equal to Rx minus Y minus XZ, and Z dot is equal to XY minus BZ. So these are deceptively simple looking, but as we're going to see, the phenomena that they contain is both wondrous and very complex. So first of all, let's describe what are the meaning of the variables and then the parameters in these equations. So in these equations, X is meant to represent how fast the convection rolls are turning over, so some measure of the convection intensity. And Y is a measure of the temperature difference at the ground and at the bottom of the cloud layer. And finally, Z is a measure of the deviation of the temperature gradient from linearity. So if there was no large-scale convection rolls, then it would only be by molecular diffusion that heat would flow from the ground to the clouds. In this case, the temperature gradient would be constant, which means a linear temperature profile. But because there's large-scale convection rolls set up, the temperature profile is not linear, and Z is a measure of the deviation from linear temperature profile. Now, in the equation, there are also three parameters, and so let's describe what these three parameters are. There is sigma, which is meant to represent something known as the Prandtl number, which is a basic measure of the nature of the fluid itself. And basically what it is, it's a measure of the ratio of momentum diffusion in the fluid to heat diffusion. Now, momentum diffusion is another word for viscosity in a fluid. So this is a ratio of like the viscosity to the heat conduction. The parameter R is the Rayleigh number, and it is the primary driving force in the system because the Prandtl number and the other parameter B are actually properties of the fluid itself, but the Rayleigh number is the driving parameter, which is given essentially by the heat imparted out from the sun. And the Rayleigh number is a measure of the ratio of the buoyancy force to viscous drag. So when the sun is not shining, there's essentially no buoyancy force, and viscosity is enough to keep the atmosphere basically static. But as the sun rises and the temperature gradient develops, then bubbles of warm air near the ground are trying to rise to the top. Viscosity is trying to prevent that from happening, but eventually there is an instability arising where viscosity is not enough to overcome the buoyancy and what gets large-scale convection rolls. And in the case of the atmospheric geometry, this Rayleigh number is proportional to the temperature difference times the vertical range over which the flow is occurring cubed. Very quickly, in an atmospheric setting, because the Rayleigh number is proportional to h cubed, any so small amount of temperature difference very quickly gives rise to an instability because h cubed delta T very quickly exceeds the critical Rayleigh number for an instability. And finally, B is another geometric measure, property of the system itself, and it's just a measure of the aspect ratio of the convection rolls. So our goal now is to explore the dynamics of the Lorenz equations. And as I hope I'll convince you, it's very beautiful and very, very appealing.